Hello, everyone. Welcome to another Wolfram Language Design Review. This is about mathematical computation functionality for version 15. And the first thing we're following on from previous meeting was we have a new non-commutative Grosvenor basis reduction algorithm. And I was trying to find out how equivalent or not that is to find equational proof. So can you define what is the difference between sort of the Knuth-Bendix reduction of non-commutative Grosvenor basis and find equational proof?
So basically, Knuth-Bendix reduction is more general. You can have arbitrary operations that they do not need to satisfy any particular rules. The only rules they satisfy are the ones that you have in axioms. Here we assume that we have two operations. One of them is both of them are associative. One of them is commutative, and there is a distributive law. So there are things that are assumed. So, for instance, this example was
Yeah, okay.
with
So
the axiom
why are
of,
we calling it non-commutative algebra if it isn't a general universal algebra?
well, people are calling different things algebra. So the standard thing algebra is so, or one name where one place where name algebra is used. The algebra means vector space with multiplication operations,
Yeah, I know.
which is associative, and this is the non-commutative algebra that the sense that we are using. So you can also call algebra anything that has some number of operations, and
Right, like in universal algebra.
yeah. So that's
Okay,
not
so can we make
what
sure
we
it's
do here.
clarified on the documentation page?
Yes.
Okay.
And actually,
It
it is
is.
defined there. So
It is
we
defined there.
specify what we mean by algebra.
So if you look up non-commutative algebra,
And we just took the latest one new because it's got some updates.
Yeah, actually, the old one also has the definition of algebra.
They both have it. Okay. Yeah.
The special non-commutative algebra. What does that mean? I don't see this here.
Yeah, I rephrased it somewhat. The special, or maybe that I'll have to.
It should have been named.
It actually that all the special things are all of them are free algebras, which you actually say here. So
Yeah, but
all we could have were the free algebras. They are all isomorphic, except that they have differently named operations.
this didn't work. This is dead in the water in this prototype build.
Do you have it happened yesterday? I haven't seen.
Okay, well, fine, but it's not working, so I can't see this. But anyway, this is not an adequate piece of documentation. So
Yeah, this is the old one. So that
okay, well, I can't see the new one. So
maybe if you use the old DocuTools.
That's even worse.
Yeah,
Yeah,
there's clearly something wrong when the prototype build.
Yeah, today's build is okay, but it came up very late, like about an hour ago, 2 hours ago. That's fine. I mean, the new build is fine, not this one.
That was spectacular.
Yes, I went through all of yesterday.
Huh.
I mean, you could use 14.3. That will be okay.
Yeah. So other than the new way of displaying algebra, the box, everything else should work with 14.3.
Yeah.
Well, I can use the 15 over head branch build.
Maybe, I'm not sure. I haven't tried that yet.
Oh.
No. I think 14.3 was safe. I did that all of yesterday.
Well, I really don't want to use 14.3 on this machine.
I understand, yeah.
Sorry. So let me go back to your okay, let's get the agenda here. Okay. So you're fixing that, but we already gone through this section, right?
Yes.
Yes.
And we talked about all those different kinds of algebras. Now we're on to other things.
Right.
Okay. Minimal polynomial.
That's pure performance.
Okay. We were talking about partial fractions.
Yes.
And
So we did, if you go, actually, we want to go look at the ref page, partial fraction rules.
Data, actually, partial fraction data is what we tried
Okay,
to go with,
fine.
but we can change the name.
Yeah, but
I'm not going to be able to open this, am I?
Oh no. Okay.
I bet if you don't use that thing, like just use the dot button, just type it in and use the dot button. That and then yeah. Yep. Oh no.
Wow. Now
What's that? I don't even know what that is. Oh, did you update documentation?
Yes.
Okay. Okay, so it's some other kind of fail, then some kind of failure with that.
Okay. All right.
Because that was a results page when it can't find a documentation page.
Yes, I understand. I'm going to try one thing here. Not optimistic.
You know what you
have an
can
S there?
what you know what you could do, Stephen, is that you could just run 14.3 or something like that and just pull up the documentation.
I'm aware. I was trying to not run 14.3 because I have a lot of other stuff in my 14.3 session that I don't want to lose.
I see.
I don't want any possibility of a screw up here that loses that.
And if you really wish, I can share for that, but that will have to happen many times today. I don't know.
Not going to work. Right. So hopefully this.
Yeah, I think you're missing an S.
Oh, well, that's what you said partial fraction data.
No, partial fractions data, because I thought it should just be the same name with a bit of, we can change that name, but yes, that's it.
So if you look here at the bottom, yeah, magnify it a bit. So the complete partial fraction, you can see the display formula there. It defines a bunch of notation, right? Alphas, betas, gammas.
Yep.
Okay. If you have a program, that's the data that you want. Because you're going to do, so if you don't have that, you have to resort to pattern matching, and you have to basically undo every auto simplification rule.
Yeah.
Right? And so that's going to take a long time to write the pattern match.
Can I make a suggestion? Why don't we call it partial fraction decomposition and have it return that association?
I mean, is it a decomposition?
What else is it?
I mean, there's not a composition here. I mean, for the linear case, we do have decomposition and factors are the same thing. But for polynomials, this is not a decomposition. It's not using composition.
Well, then partial fraction form or something? Partial fraction.
Rules, raw form, all are fine. What do we decide?
Partial fraction elements.
Well, maybe we can use decomposition and sort of say that that's like it's not an actual decomposition, but that's what people call it.
Yeah. I think I like elements a lot better because it says what the elements of the partial fraction are.
Oh, I guess.
Yes. But now, so then we would or would not have the function partial fractions.
We
would. Oh yes, that's
for, that's great in a learning student scenario if you just want to admire the formula, that kind of thing. But if you want the pieces of it to use it for computation.
How does that relate to a part?
Yeah, so a part has got will not do a complete over the complex. So if you do a part of 1 over x squared plus 1, it won't do much. If you partial fractions, it'll do the actual complete partial. So that's the one place we are breaking apart, and we can't afford to do that.
So here, if I say partial fractions,
1 over, yeah, this is the simplest. 1 over 1 plus x squared, comma x. Right. And if you do apart, it's going to do nothing.
Yeah, that's fine.
Yeah, so the point is that this is what a lot of people require. Now, what the new function does, it also gives you flexibility. So if you say extension goes to none, you get back to apart. And if the extension goes to something else, it'll do the right thing for you. So it's very flexible, covers all the cases people ask for.
Okay, but then this function just does this, and partial fraction elements would be the thing that gives you the association.
The data,
the pieces which you can,
the details, basically.
Yeah.
And so a typical piece of code will say partial fraction elements of blah.
Yeah.
It'll either compute it and then it'll say sub whatever, or it'll have a third argument which extracts that element specifically right there.
Exactly.
Okay, and partial fractions itself would not have any of that extra tooling. It will just be the
right. So the way we had packaged it originally is that partial fractions did both. The default element would be the sort of that display form. And now we split them into two functions. So the partial fractions is just the display form, basically. And the other one is the data version, where you get sort of things that you call.
I wonder whether there are other things where we might want to use this elements concept. I mean, one that is always kind of annoying to me is factor integer, which, gives this thing which is a structured form. That's not a good example, really.
Right.
But anyway,
it's clearly, and I'm sure you did this, there was some thought put into that for some of those functions early on. Clearly.
Yeah.
But it gets, the more complicated things get, the more elements there are, basically. And this is one that we haven't returned to until now, but it's one of those long wished for things. And I don't know. I'm sure that I've implemented this about a dozen times.
So have I, for lots of internal code.
Right.
Okay. All right. Well, good. We have a solution here. Okay, let's move on. Matrix algebra. Now, we were talking about
what the workflows are. What do you do? What are these things used for? What are the typical workflows? Is that this one of the things? So I meant to prepare a little presentation so you can see that, since you're not kind of a user of that.
Yep.
So these decompositions, what they do is that they break down a matrix into structured, simpler matrices. Okay, and there are basically three groups of decomposition if you think of actual sort of vector spaces and matrix stuff. And there are things related to linear equation solving, and those are LU, LDLT, Cholesky, essentially. Okay. Then there's a group related to least squares, and those are basically QR and SVD.
Okay, just so I understand, something like LU.
Yeah.
If you were going to just repeatedly solve some linear equations, with different, it's like an inverse, like the equivalent of inverting a matrix and so on, and just applying the inverse matrix. I mean, why would you use the decomposition? Why aren't you just saying, I want to solve my equations? Give me something that will solve.
We invented, okay, me, you, many years ago, this idea of linear solve function. And what's stored inside of that is an LU decomposition.
Yeah.
Because what you then have is so you can change the right-hand side. So you want to apply it to many right-hand sides. So then it can use this much cheaper.
I get it. But so why are we providing? Isn't that the workflow people want? why do they independently want the
So
LU
independently you want it because we don't know all the use cases for which you need these decompositions. You need that developers need this. Okay, people that write packages and frameworks in the Wolfram language need this.
Okay,
because we provided.
So how do they want it packaged? We're returning right now. LU decomposition returns this stupid single matrix thing, right? Rather than,
and that's
it returns. It returns.
It's the stupid single matrix
with L and U
packaged into one.
A permutation list and a condition number.
Right. So what we've since done, okay, we defined, and we are unique in this, defined structured matrices. So we have an upper triangular matrix. Now, if linear solve gets an upper triangular matrix, it knows that it can use the much cheaper algorithm called back substitution.
Yeah.
Okay,
Right.
if it's got a lower triangle, similar, use a forward substitution algorithm.
Yes, I understand.
Okay.
Okay.
So we have those workflows for our solvers. If they can use the structure, they will.
I get
Okay.
it. The question is, what does LU decomposition return?
So it should return, ideally, it should return structured matrices. You won't waste any space.
We need,
if
we have a compatibility issue there. So the
Right.
question is,
we do have a compatibility issue. But I do think that we should change the default, and you can always get back the legacy behavior if you so choose with an option
I'm very
setting.
nervous about changing the default. Okay.
But
so,
we've done that in many things. But there is an easy solve. If you want the other thing, you change the option.
Why don't you look at all the code we have and see how much stuff would
Okay.
break if we did that? Did somebody do that already? Somebody do that or not?
I mean, we'll take care of our own code.
No. I'm not asking that question. I want to know how much code, taking our code as a sample, how much will break if we change that? Okay.
Yeah, we can do that, but we haven't.
So I mean, one thing, I mean, technically this, right, what we're doing is a PLU decomposition, right? Because we're including the
Sure.
permutation matrix.
Yes.
So we could have a new function called PLU decomposition.
No. It's never called that.
I think
It's sometimes called that.
I don't know why you guys keep insisting on this, but you're obviously not users of this functionality.
I don't care. We cannot make an incompatible change just because
we have done it a gazillion times,
no,
and it's not a
haven't.
hard.
No, we
yes,
haven't.
we have.
No, we haven't. Not
remember
no,
the graphics change
in version 3?
6.
The change that we had a lot of tooling around that change.
Mm-hmm.
Remember that? If you put a semicolon after a plot, it turns red. Right? So what could we do here to indicate that issue? How would we do that here? I think it will just silently fail. Okay, so
I mean, we
right
could
now,
start issuing warnings every time you call this function. If you want the old behavior, set this option.
No, that's not a good solution. All right, so what is it that you propose that it should return?
L, U, P.
And that's the permutation, and the condition number is
but
not.
nowadays we want a permutation matrix as opposed to a list.
Okay, so what you want it to return is an L matrix. So these are all structured matrices.
Yes.
Okay, what about the condition number? What happens?
And then a condition number for compatibility.
There is no compatibility.
No, but the condition, but the same result is just packaged differently. It's still a condition.
Let me make a suggestion, which I think would solve this. Why not return a list of the L matrix and the U matrix, then the P, then the condition number?
That's brilliant. I really liked it.
Well,
I mean,
then you at least have a fighting chance. I mean,
we can live with that. Not
but hold
great,
on. Maybe there's an even better idea. Okay, you've got two structured matrices.
Mm-hmm.
What would you do?
3. P is also structured.
No, I understand that, but I mean the L and the U.
Mm-hmm.
Okay, what would you typically feed the old LU packed silliness into? What would that go into? Anything?
Nothing.
I mean, typically the first thing you would do is, write L is lower triangularize of the result, and U is one diagonal is identity plus upper triangularize, or maybe the other way. I forget.
Yeah,
which
so
way
there
it's
would
packaged.
be codes that do that. That try to construct what we
I mean,
have here now.
If you look at the current ref page,
but
you'll
the other
see
thing,
that
when you do that, when you do those upper triangularize, if that now returns a list, you would still not get the benefit of the structure. You'd still fuck away the structure.
I know. Okay, so the proposal now would be to have a second argument to LU decomposition, which says which elements of the LU decomposition to get, the lower, upper, or permutation matrix, right?
No.
Well, I think we should do that.
There's an option that says like what form you return it in.
Target structure.
Yeah.
What?
Well,
we introduced target structure for a lot of functions, right? As we introduced the structured matrices. Like an identity matrix is really good to return as a sparse one. Like a million by million identity matrix.
Okay. Let me make a suggestion here. So I'm beginning to realize, okay, the truth is that the old LU package thing is pretty useless.
Yes.
Right. Yeah, Stephen, if you open the LU decomposition page and just look at the first basic example.
I have it open. It's right here.
Oh, sorry. Sorry. I'm traveling, so I'm on a small screen. I didn't notice it. Yeah.
Okay.
Right. So yeah, the first thing I do is lower triangularize and add the identity matrix and upper triangularize.
Okay. Well,
but you can still not use them very well.
I'm softening on this point because I think what we had before, nobody's going to have used it because it was pretty useless.
Exactly.
They're going to have done a bunch of processing on it.
Right. And they would have written their own backward substitution or forward substitution algorithm, which is, not easy or efficient. I mean, it's easy, but it's not efficient.
I bet it will break some numerical analysis textbooks.
It'll break my course, the Lenovo course, because I spent so much time explaining this stuff, the lower triangular, upper triangularize in the course. But that's fine, Stephen, because I think compare that with going forward where everyone gets the right thing all the time. I think that's for me. It's just
no. It's obviously the right thing that we're doing now.
Yes.
In the future.
Now, in terms of the packaging of the L and the U together in a list, I don't know. It's a question of what happens with the other. I think that's a slightly.
I think that all of them should be flat. If this one is an exception because you guys are so worried, then we can live with it.
No. Why should they be flat?
Because you want them all. Why would they be a structure like that?
Okay. So then the suggestion.
The only thing you don't want typically is the condition number. And maybe, sometimes you do, but most of the time you don't.
But it's computed along with the LU and permutation, right?
Because you get it for free. It's not even the correct condition number. It's an approximate condition number that you get for free.
Nick is suggesting a decomposition object that automatically unpacks itself. I mean, that is a bridge we should at least discuss. Okay? In other words, if there are enough decompositions running around the system, does it make sense to introduce a decomposition object that can be poked at?
What would it do?
Just a single object you can poke that has stored the result, but it computes it once, but then you poke at it to get the different elements that you might want.
I think if we didn't have, if we didn't have the structured matrices, probably that's what we could do, because then we could kind of fake it there in some way. No, you still would need the structured matrices to actually make it work.
Yeah, you would. But let's just think about that.
I don't see what you really gain by that, right? It's not like
it seems like one level of interaction that we don't need.
Right.
Okay. All right. So look, with this thing, my suggestion would be that it gets a second argument that can have, that could be association.
So should we do that for all other functions that now says?
I think we should do it for these decompositions where there are.
Well, some of them take arguments too. Like you want, the thin or the full or the, only k eigenvalues or eigenvectors, and some of them have arguments.
Okay, well, let's look at that. Because I think that this thing where you're returning random kind of disparate objects as the result should have the possibility of returning them in an association where they're named keys for those disparate objects. I mean, it's a different thing. If you say, I want the eigenvalues of this matrix, everything in there is an eigenvalue, and it's not. It would be stupid to have keys.
But we also have eigensystem, right, which
know.
returns a list of two things.
Yep, I know.
So,
I mean, 2 is a manageable number, but the time it's 4, I don't think it's very manageable. I mean, but the claim is for many of these decompositions that you only need them all together, that you never need just the L.
Yeah, yes, pretty much.
Right. Like QR, I mean, you need the Q and the R. SVD, you need all three, right? Maybe there are some particular examples where, right, and when you only need the singular values, right, we have singular value list for that case.
Yeah, so we've built those service functions for things that one might need that are more special. There's a bunch of things that are basically derived from these. So if you do matrix rank, that uses an SVD for an approximate matrix, and that's absolutely the correct way to do it. But you don't get the SVD, you get the actual rank, which is an integer.
Where's the new version of this? Can I see it run?
Yeah, LED comes to new in prototype.
Oh.
Isn't it just LU decomposition?
I mean, it's just LU. If you're running the example, then it's just LU decomposition.
To run it, you mean?
Yeah,
Where
just
are
to
the
run
examples
it. Yeah.
here?
Sorry, no, but I think there's a ref page, so I didn't put. But you can just take the same example that's over there, the one that you have with you on the left-hand side. I mean, so you'll start seeing the difference in the prototype build. There you are. So you get low triangular
LUP.
It's nice.
So I think it's very clean. The only question was backward compatible, but if you agree on that, then this is very nice.
All right. I hope I will not going to regret this. I'm reminded of polynomial mod.
Yeah.
Okay.
Famous example where we went back and forth twice.
Yeah,
I think that we have, I mean, truly we have the best design here now, because no others have sort of structured matrices.
Yeah, I understand. So is there an option, a target functions option?
Yes,
or something?
target structure. And if you do target structure goes to classic, you'll get back the exact same input output you had in the earlier version. I mean, 14.3 classic. There you go. That's it.
All right. I'm sorry.
What other values of target structure does it accept here?
Right. So then you got automatic, which is basically the same as what you say, lower triangle, upper triangular. You have structured, sparse, and then classic. So if you do structure again, you get back, of course, the same, yeah.
Why don't we have a dense one?
I think that's there as well. I think we try it. Should be dense, should be there, but we can. I'm pretty sure.
I think we've used.
Yeah.
Okay.
Yeah, okay.
Oh, although it's returning a permutation list here, not a.
Right. So this is something we couldn't quite decide on. So what should be? I mean,
I think it should be
matrix.
This, but with a permutation matrix.
I think it should be a matrix too.
Okay, so then should be a matrix. That's fine. So we didn't have a good decision on that. Sorry, but
yeah,
me and Danny, but we didn't discuss.
All right. Okay. We got somewhere here.
Okay.
So that means that we have a good future path for all this. It's
fine.
We clear the workflows.
Yep. What's this? This is the WFR that it came from.
Yes. So we are trying to make sure that whatever is valuable over there goes into the system. And
okay. Please make sure when that's happened that we put a stripe on the WFR.
Okay.
You do know that, right?
I'll ask Danny, but
there's an up-to-date ref page for polar decomposition. I haven't looked at the other. I haven't verified all of the other pages, but
the name polar decomposition. are you sure that that isn't confusing with respect to complex numbers and things?
I don't think so.
Look at the first note here.
There's analogous exponent. What? There's analogous to.
Yeah,
it's
okay, so
analogous
I
to.
missed the word, sorry.
It's similar to, or analogous to.
Okay.
Yes.
It's my least favorite decomposition, but for completeness, we should probably have it.
Why isn't this in structured matrices?
It should be. We'll return to that.
Okay.
So polar
We
decomposition.
we need to do a pass over all the decompositions now and do this consistently.
Okay, fine. Yes?
Do we have a structured unitary matrix and Hermitian matrix?
Yes.
Hermitian, I'm not sure. Unitary we do.
If we don't, we should add it eventually.
Okay. So one thing on next release is to have target structure uniformly tackled
Yes.
for all decomposition. Now that we have enough of them, so to speak.
Yes.
All right. So we've agreed by default, they will return structured matrices. All these decompositions are all, cogs in the machine type
Yes.
thing. True
Yes.
statement?
True
Is that
statement.
true of all of them? There's
What do you
none
mean by,
that's
hold on, define cogs in the machine.
Well, I mean, like singular value list is not a cog in a machine. You just want the singular values.
I mean, okay, depends on what your goal is, what you're going to do.
You're arguing that LU decomposition, for example, it's not the case that somebody says, oh, the stability of a control system is determined by the permutation in the LU decomposition.
Right.
Something like that is not true.
No, it may be not that particular thing, okay, but
yeah,
because that's determined by eigenstructure and other things, right?
Right.
But yeah, so the thing with these things, they are intermediary layers that branch off to a huge set of applications.
That's why I'm asking you. Do the things here have an independent meaning, or are they going to be fed back into essentially a numerical analysis algorithm?
Well, both. So sometimes,
right.
Most of the time they're going to be fed back into something. Okay, that's I don't know, 70-80%
but like the condition number is something that sometimes has an independent significance.
Yes, and we will add condition number in the next release as an actual function that actually computes the correct condition number.
Yeah, so we have a design for it, but we didn't quite finalize it. It requires a bit more work. So
but what I'm to understand is that anything whose name ends in decomposition is something that is going to return by default a list of structured matrices, structured matrices in particular.
Right. Exactly.
Okay, so
there is a bunch.
Loeb decomposition is certainly not of that kind.
Right. I mean, it strictly is, but the way this one is done is not that way.
Jordan decomposition?
That is this way.
Okay. Obviously, polygon decomposition is not, but
obviously not, right?
There
are many decompositions in the world.
Cylindrical decomposition is different thing.
Yes, cylindrical decomposition. Yes, there are more.
Decomposition, which is of integer matrices, isn't it?
But this is of this type, and it has the structured matrix there is called is unimodular. That's the property it has. Okay. We don't have that yet as a structured matrix form, but we should probably add it.
But wait a minute, unimodular just means determinant 1, if I'm not mistaken.
Well, for polynomial, it means determinant constant.
Oh, and Smith decomposition involves polynomials?
No, there are two of them.
Polynomial Smith decomposition involves polynomials.
So unitary means different things for both those. Well,
not unitary, unimodular.
Unimodular, I'm sorry. Yeah.
So a unimodular polynomial thing can be stored more efficiently, can it, than the dense form?
I don't think so.
So what's the point of having the unimodular, decoration?
Well, some properties of it, but we have to research what are the things that we can now do more efficiently. That's what we do for all structured matrices. Like, is there a big algebra of things that sort of...
Okay, but I want to come back to the question. A star decomposition function.
Yeah.
What does it return?
A list of matrices.
Which might or might not be structured.
Right.
All right, fair enough.
But our goal should be gradually to have them,
right.
mostly
But
be
that's
structured.
okay. That's a not a that's a compatible change because the structuring is just packaging, and if you
Yes.
actually applied functions to it, it better do the same thing as the unstructured version, right?
Which it does, yes.
Like part extraction and all those kinds of things.
Absolutely.
Yes.
And dimensions and all that.
Yep.
Okay.
So the condition number in LU decomposition somehow doesn't fit this pattern.
No, but I agree, but it's not that it doesn't do any damage to keep it for compatibility's sake.
Yeah.
So yeah, it doesn't fit this, but it doesn't do any damage either.
But just so I understand, in the algorithm for LU decomposition, the condition number comes out as part of the algorithm. Yes.
So it's for free, and it's
Yes.
a decent estimate. So if you worry about something blowing up, you can check the condition number. If the condition is 10,000, probably things won't work.
Yeah. Right. Okay. All right. Let's see. Where do we go next? I don't know why that other one. Okay. Special functions. So let's just look at what we're looking at here because we've got.
And the rest is mostly related to special function. I guess that's the really last big piece. So there are 3 multiple functions. One updated
what version is this that I'm running here? Okay, this was 14.3. Do I want to run in 14.3? No, because I actually want to run some things. So let me exit that. Let me exit that. Let me exit this. Exit this. Okay. All right. I want to talk a little bit about calculus before we come back to special functions.
Sure.
Okay. Great. I want to see this for simplification.
There should be thousands of examples if you're lucky, which are new with this stuff and which are new or improved.
That's great. Lovely.
And we check them also. It's all 100% guaranteed to be correct.
Yeah,
So even if it's an unreliable algorithm, the way we package it, it's not unreliable because we validate.
Yep. Are we running it in a separate thread?
No, I don't.
No, I mean, go ahead.
Actually, we might.
I can check with Julio, but I
think
let's
check that because actually that should have been an accelerated neural net. So that probably does run separate.
I mean, we could run the regular algorithm at the same time that we're trying to do the.
Oh, we're not doing that.
Oh no, I decided
we're not doing that. We can't really. We need a little bit better top-level tools to do concurrency.
Well, that particular one we certainly could do with a local, I mean, I think we were thinking about how to do that. I don't think that's an undoable thing.
I don't think so either, but I wouldn't,
Okay, but I mean, if we're going to, let's define that as a project to make it so that we can do things like that. I mean, obviously parallel try.
So we did that. So sum for version 7, we introduced that for sum. So sum can do that, parallel try.
By default?
Yes. No. You got to say method goes to parallel.
Which nobody will ever do.
No, actually, that method option has never been used. I mean, if we put a lot of work into it, it's beautiful, but no one uses it.
Well, but maybe we should switch it on. Now that people routinely have multi-core machines, which they didn't at the time of version 7, maybe it's time to switch it on.
That leads to another thing that I'm about to bring up, but not for this release. So we need to do, so there are people that maybe are responsible for servers, like the Wolfram Cloud people and others. They hate it when you suck up every core on that machine. Then there are people like you and me that have, high core computers, and we want them to soak up everything and get the job done.
Yep.
So I think we have this spread of use cases, and we got to get users a way to set what policy they want to follow.
Yes, I agree. Let's have a meeting specifically about this. This is, I think, going to be fairly straightforward. We've talked about related things before. Let's just do it.
Right.
And let's
so
have it be the case.
We need to do that. When we do that, what that will do is to set us free, to pursue
I agree,
this.
but let me make a comment about that. One of the stupid things right now with parallelism is like I have a couple of hundred cores, but they're not all on the same computer.
Right.
And every time I try and do anything in parallel, it tries to launch all my cores. But the truth is, for something like, I just want to run these multiple algorithms together, I only want my local cores. I would never want to launch it on a remote machine.
That's a good use case. So Charles should be in this. We have started working on this already, okay?
Right, fine. But let's have a meeting specifically about auto-parallelization in algorithms. And can we please add that to GPL? And yes, fine.
So this is part of our performance pursuit, okay?
Yep.
And better resource utilization.
Yes. Okay. But I hope we've started on the simplification angle of this neural net.
Yes, we have.
Yes, but it's not for this release.
I understand. This is good. Okay. I mean, basically, the neural net thing is going to happen in constant time, and it does what it does. And if it works, great. And if it doesn't, we go back to the traditional approach.
But of all the things, that's the one thing that doesn't take up much time. It's a very efficient net that it's wonderful. So it's compared to, it's worked really well.
Okay, well, good. Let's figure out where else we can do this.
Yeah, we have 2 or 3 projects lined up already for the next release, or at least next 2 releases.
Oh, yeah. That actually relates to those polylogs.
Okay.
Right. So I didn't put an example because it's kind of covered a little later under asymptotics. It's very similar. So basically, point is you have these differentially. So honestly, all that is borrowed from the polylog stuff, but it had to appear separately for reasons of administration, right? So
I think if you open under asymptotics,
you see the asymptotic desolve value example, which is so typically you only look for asymptotics of these Feynman differential equations or what you want to call them. But there are some cases where under some nil potency requirements, you actually get back exact solutions, which I have not seen too much in literature. So that's what desolve value does. It will pick out those cases where you can actually give it not just asymptotic, but exact solutions.
But this is asymptotic desolve value is something we already had, right?
Yes.
Right. But this would bog down with iterated integrals in the solution and things like that.
Exactly.
With this, that just sails through and scales.
What is that? I should know it, but what is the definition of a Fuchsian system?
Right. It's single order poles.
Yeah.
I see.
So you never see a square over there. You never see a square over there in the denominators. But that's just a discrete Hilbert transform, which there's some very nice applications which we've figured out and we contribute to example repository, medicine and seismology and all that, which you can't do with the exact one. So a fair amount of work is
the discrete Hilbert transform is like on numerical data, like a discrete Fourier.
Yeah, it's just like Fourier actually. You're right. So we have discrete Hadamard, is it? I think that's the other one that we have. So this one is similar. It in fact relies on Fourier, but it's a little harder because it's only in one direction, like half line, not a full line.
Cool. Okay, let's come back to the polylogs.
Yes.
So you see some of the benefits down there, but there's more coming in the next release too.
And I assume that multiple zeta is what we want rather than a list. I guess zeta is a listable function, so we can't.
Exactly. That killed the whole. It would have been wonderful if it were not, but you can't do that. Exactly. And these are typically called multiple zeta values, but we can't use that. So we say multiple zeta. And you see examples over there. These Euler sums, there are plenty of new ones which we can do because of the multiple zeta available now. And the traditional form might work if you want to try it.
I wonder if the term multiple harmonic number is the right term. I mean, or is it multi-harmonic number?
I think we are aren't we using multiple somewhere else? I mean, like in other parts of the system. I've not seen multi anywhere, honestly, in the literature.
Okay.
Multinomial.
Multinomial. Well, yeah. No,
What
it's
the
only
heck is a
us.
multiple quasi-zeta?
It just leaked into system somehow. I don't know.
Multiple hyperharmonic number. What's that?
That's another new function.
No, I think this multiple harmonic number. I think we only have a hyperharmonic number, so that's probably from somewhere else. We have a hyperharmonic number. We don't have
Oh,
a UN prototype, right? So it's probably just leaking from somewhere. I don't know
I
from
see.
where.
Okay.
So I think uniformly people use multiple zeta. They don't use multi-zeta. So I feel this is right nomenclature, but if you really want, we can check.
I think I agree with you. I think that at least from when I read it, I read kind of this literature maybe 10 years ago, 10, 15 years ago. This is not the latest, but
There's quite a big group at Risk and places there which have done a lot of packages. We are nowhere close to them in sophistication, but we've tried to absorb the basic ideas.
Okay. What else to look at here? I mean,
yeah, I think this is really well developed. Honestly, not because I didn't do it, but it's huge amount of testing and beautiful example. Amazing how.
what's the difference between a generalized polylog and a
Right,
multiple
good point.
polylog?
So it's a question of poles. The generalized polylog will allow arbitrary poles, and harmonic polylog has got a slightly special structure where I think the first one or two poles have to be at zero.
Wait. Multiple polylog doesn't, I mean, in this one, we have shifts as well, right? Is that right? Here, whereas this one
Yes.
doesn't have shifts.
Yes.
yes.
It's just multidimensional.
Yes,
Right.
exactly. So that's the direct generation of polylog.
Sorry, generalized polylog is both multidimensional and can have its poles shifted.
Generalized polylog. Yes. So just one.
well, the argument for one thing, the argument structure is different, right? Multiple polylog wants equal length lists, and generalized polylogs wants a scalar list.
So Stephen, I mean, sorry, go ahead. Itai.
Well, that was my whole statement, right? So I can't give more insight, but as the person who did the typesetting for them, right, the generalized polylog only takes one list, whereas multiple polylog requires two lists.
Exactly. So multiple is in the second argument. That's what the multiple means over there.
Okay, but multiple polylog is multidimensional polylog, basically.
Exactly. It's the
Generalized polylog is what?
Okay. So it's called polylog, but it's the extension of the integral definition of a polylog.
Okay, so just to understand, I mean, like we go from dilogarithm to trilogarithm to whatever.
Exactly. Yeah.
And this is doing that, but every level of
Integration.
Right, of whatever it is has a different shift to it.
Exactly. The pole, I mean, you might call it shift a pole or whatever, because that appears as a pole in the denominator.
Yes.
And then the harmonic one is a little special because I think the first pole has to be zero. That's just what the literature says. So we want to make sure so the generalized one is called Goncharov and the harmonic one is called harmonic, but people call it the Goncharov polylog.
I understand. The harmonic one doesn't go to infinity, right? It's a summation in the in the standard polylog, x to the n over whatever it is, x, my God, what is it, over n squared, right? That's the ordinary polylog, if I remember correctly.
So ordinary polylog will be z raised to n over n raised to
squared.
Yeah.
N goes to infinity.
Yeah.
That should be an ordinary dilogarithm. Yeah, right. So the harmonic number analog of that is n goes to n1, right?
Yes.
And then, so there should be a harmonic number. I'm confused by this. This form here As a multiply nested harmonic. I see it. No,
It is multiply
Yes,
nested.
yeah, but right, okay, but if they, I see the limit. So the multiple harmonic number.
with
You
the,
see
with the
how
infinity in the
they,
first argument should, I think, give you one of them.
it's kind of like a triangular summation region. See how they nested the
Exactly.
variables?
And if you did,
Oh, they're nested like that.
Mm-hmm.
Okay, but wait a second. Are there any other generalizations that you are thinking of adding in the future?
no, not in this direction. I mean, there's things like Epstein zeta, which
Yes.
is slightly different, but we fell short of, we didn't get good reference. I know you
used
got
Epstein zeta.
Yes, so that's where you
40
got
years ago or something.
the thing from your paper. That's where you started off, but it's not so well used in the modern like setting. We have not seen a lot of literature in the
Well, I
last.
mean, there's also Madelung sums and the whole lattice sums business, right? Which is related to that.
Yes, so the hope would be that some of this would give us a handle on more lattice sums. That's the
But I
hope.
mean,
But
I think we should have a function since we have a representation of lattices, and we're about to get crystallography. You know, lattices, actual crystals. Representation of crystals. It would be lovely to be able to do a lattice sum over an actual crystal lattice.
so you have a new function called lattice sum.
So you have like a vector space,
Yes.
vector basis, and then
yeah,
that's
right.
the lattice.
Like we have lattice data gives us, if I say,
Mhm.
There are my whatever
Basis.
basis
Yeah.
vectors.
Mhm.
Wouldn't it be nice to be able to do a lattice sum over that?
Mm-hmm.
And that would give us, ultimately that will give us all the Madelung sums, zeta function, Epstein zetas and so on. Right.
I see.
have to run.
As special cases.
Yes. But I think that's what we should be going for as a lattice sum type function.
Okay. I did think of it. I think I'll pass it on to the giant and this developer, because I think we had to stop somewhere, so we stopped over here.
No, I agree. But this is very nice.
Thanks. Yeah, it's very deep. I was surprised how.
And how much? There are obviously series expansions of all these things. There are presumably asymptotics.
There's a lot of simplifications. Yeah, there's asymptotics, but there's a lot of simplifications. They're called shuffle products and stuffle products.
Yes, so that's how you do. You can simplify very large expressions or auto expand and all that. One last thing is that there are also analytic continuations, which like in terms of sometimes lurch fire, whatever. So we've tried to be as complete as possible. Unless a parameter is clearly integer, we have tried to have extensions to the complex plane in all cases.
Sounds good. And the numeric attribute is correctly handled for these functions that have slightly more exotic listability and so on.
Yeah, so we went through that Adam, I think, a little bit this week, and I'll better check about that. Yes.
Okay. Sounds good. All right. Great stuff.
Thank you.
Talk to you all soon. See you later.